Let's do LeetCode 1115, print FooBar alternately. This is actually quite an interesting problem, kind of an intro problem to concurrency. So we have two threads, A and B, and they're going to call two different functions. Thread A is going to call foo, thread B is going to call bar. This is calling functions on the same object, which is being passed into these two different threads. We're going to want to print FooBar n times, and note the ordering foo first, then bar. We're given n as part of the input. These two threads are being fired asynchronously, one of them calling foo and one of them calling bar. Let's visualize this a bit better. So with thread A and thread B on the y-axis-ish and time on the x-axis, we can kind of see how interleaved calls of these functions are then synchronized over time in a single process. So we have the main process somewhere. That's going to be the thing that runs these two threads. And these function calls could look something like lowercase b denoting a function call to bar. And this could happen many times before the first function call to lowercase f denoting foo being called. So our execution could look something like this. We have 4 calls to B. We need 2 more calls to F as time progresses. Even though all the B calls here happen before a lot of the Fs, we need to make sure that we don't print out bar before foo. So before print bar, we need some sort of mechanism to wait, and let's denote that W. We need to wait for the function call to foo first so that it occurs, and then only after that can we call the function call of B. And we also need a way to make sure the next call of B doesn't occur before the next call of F. So how can we block the next call of B on the next call of F? We want to print foo first, and then after that, the waiting will result in print bar occurring afterwards. Something we can realize is we have two threads. And something that can help us synchronize these two threads is the barrier in the threading library of Python. Python has a lot of concurrency mechanisms that you can use. We're going to use barrier. It's a bit of a high-level entry point, but it's a pretty easy idea. Overall, you give it the number of threads you want to synchronize or the number of asynchronous calls, and there's a wait method. The wait method waits until the barrier is called that number of times before progressing, essentially halting the execution of both threads until the number 2 has been achieved, so 2 waits have been achieved, and then the execution will continue after that. So it makes sense to put a wait after print foo so that the foo thread A can synchronize with the bar thread B, and it makes sense to put a wait right before print bar to make sure that synchronization happens before print bar occurs, so in the console output it prints foo then bar. There's another lower level implementation which I think is interesting that I think we should go through using semaphores. Semaphores, you can imagine, are a count of a constrained shared resource, count being some number n, where if I acquire that semaphore, I decrement the counter by 1, and when I release it, I increment it by 1. So we'll make these semaphores, SF denoting the semaphore for foo, and SB denoting the semaphore for bar. We want to make sure that we acquire the semaphore for foo here, so that we know we only print after we've decremented that resource. So if we want to print foo before bar, we want to print foo bar, so it makes sense to start with semaphore foo equals 1, and would make semaphore bar 0. Before printing bar, we need to acquire the semaphore for bar, just like we did for foo. When we print foo, we held this semaphore for foo, and we never released it. In order to enable print bar to happen afterwards, we'd need to release the semaphore of bar after printing foo. So when we require it goes to 0, we then print foo, and then we release the semaphore of bar, making that 1. Similarly, in order to print bar, we needed to have acquired the semaphore of bar. Then we can execute print bar. So when we acquire it goes to 0. The semaphore of foo is also 0 because we acquired it before but we never released it. So we need to release the semaphore of foo after print bar. Let's jump into the code. So we'll start by importing threading. And just like we said before, we'll set up our barrier to synchronize these two threads. We said we needed to wait on the barrier to synchronize the threads after print foo, so that foo gets printed first. And we can do that with barrier.wait. We then need to also wait before bar gets printed, so that foo occurs, then we wait for the two threads, then bar occurs. So we'll do another barrier.wait. And let's run this. So we got an error with the indentation. It looks like we're a mixture of tabs and spaces for the methods print foo and I assume print bar. So let's get rid of those and just tab them back. Let's run it again. And we're good. Cool. We can submit this and it looks like it works. The runtime is a little bit slower, only being 10%, but that's a little bit variable. We can show this with another submission. And this time it's a little bit faster, so that's the variance. Let's also implement the semaphore solution. So let's get rid of the barriers. And using the same library, we're going to make two semaphores. We said we would start semfoo with 1 resource, so let's do that, and initialize sembar to have 0 resources. We need to acquire semfoo before printing foo, and release sembar after printing foo, so that thread B can then acquire the semaphore for bar. And in the case of bar, we need to acquire the semaphore before printing bar. And similarly, afterwards, we need to release it so that semfoo can be available at A when it tries to acquire it. So let's release it after print bar. And that should be it. We can try run this. Cool, and submit it. Awesome. The submission seems to be a bit slower. We can run it again similarly like before. And it's a bit faster, being 46%. We can look through the prior solutions to see if there's a big difference in the runtime. There really isn't. It's around 20 milliseconds. We did a semaphore approach. And we can see here, this one did a lock approach and that did a semaphore approach, very similar to what we did, essentially the same thing. So the difference in runtime is not because of our code, it's just some variance on the machines it's running on. Hope this was helpful. Catch you next time.